All right, can I verify that you can hear me online, please? Maybe not.
We can hear you.
All right, thank you. Okay, so don't forget we have test 2 on Thursday. Okay. Chapter 2. It's small, everything about second order differential equations, homogeneous, non-homogeneous, and spring mass. Okay. And yesterday we started section 3.1. Just the basics of Laplace transform. Okay, so if you're given a piecewise continuous function f of t, where t is time greater than or equal to 0. Okay, so progressing in the positive time axis, then we can define the Laplace transform of f of t as the integral from 0 to infinity e to the power of negative st times f of t dt. Where this s is the output parameter, which is actually a complex frequency term. Okay. So those of you who are dealing with signal processing and other things, actually going from a time world to a frequency world. The time world is one-dimensional. Okay, the frequency has two components, the amplitude and the phase, so it's two-dimensional. That is why it's a complex frequency. Okay, and that is what helps us kind of break it down and understand it better instead of being just the original signal. But this gives us a function of this frequency s, okay, and that is what the Laplace table is kind of listing it. Instead of you doing this every time, okay, there is a table of Laplace transforms which you should have when you do chapter 3. We derived a couple of those, okay, and the important thing is that it's additive, which means that if you have two functions whose Laplace transform is given to you, you can add the individual Laplace transforms. Okay, it's going to be a times f of s plus or minus b times. It's a pretty obvious property, but then it's not multiplicative, as you can imagine. It's a improper integral. Okay, you cannot really multiply the respective antiderivatives. And it also works backwards. If you have the Laplace transform, you can always go back and retrieve your function. That is what you're trying to do here, actually, because we don't want our answer in terms of some mysterious things, right? We want everything in terms of what you started with. So the inversion process is the more algebraically intensive part of this problem. Okay. And we were looking at a few cases yesterday. We were trying to see how to manipulate the terms so that we could match the table. So it's usually means partial fractions. That is probably the most popular one because it helps us kind of decompose or disintegrate products of terms into multiple individual terms. Okay. And we'll also see one example of completing the squares in today's example. Everything towards the goal of trying to match something in the table, and that way we could kind of go back and retrieve the function f of t. Okay. So I think we just started doing an example yesterday when we ran out of time. So let's just go back to that and finish that off. Okay. And we'll do an example with completing the squares, and then we'll start doing initial value problems using Laplace transform. Okay. So before I do that, do you have any questions about anything, about the test or about anything that we covered yesterday? Any questions? In class, online? No? Okay, so let's look at yesterday's example. You might want to just remind me. I think it looked like this: s times s minus 2 to the power of something like this. Okay. And I think I mentioned that for terms of with repeated factors, the partial fraction is a bit unique. Okay, so you have to write one for each term, and this is going to be the Laplace inverse of a over s plus b over s minus 2 plus c over s minus 2 whole square. It's not really bs plus c over s minus 2 whole square. It doesn't work that way. Okay. Derivation of this is pretty simple if you just if you want to really know why that is the case. Okay. So it's typically this one over s times s minus 2 whole square. So write it as a over, and you can call this as u. Okay. You have b u plus c over u square. Okay. That is what you're familiar with quadratic terms, right? Bs plus c. So you can write u equal to s minus 2. So this is a over s plus, this is b over u, and you have c over u square. And u is s minus 2. So that is, why we have the special thing for repeated factors. Okay. It's a very simple algebraic reason, but sometimes it bothers the students as to why that is the case. So that is why. Anyway, back to here. So let's do our usual business of comparing the coefficients, of clearing the fractions. So 1 over s times s minus 2 whole square equal to a over s plus b over s minus 2 plus c over s minus 2 whole square. To clear the fraction here, you have to multiply throughout by s times s minus 2 whole square. Okay, that is the least common multiple. S times s minus 2 whole square, and that gives you 1 equal to a times s minus 2 whole square plus b times s minus 2 and c times s. Okay. I'll do it right. Multiply s times s minus 2 whole square. The first term has an s. Yep. And it's easy to see what can be done here. You can set s equal to 2 to shut off the first two terms. Okay. So that will shut off term 1 and term 2 and will give you c equal to a half. And similarly, if you set s equal to 0, it will shut off terms 2 and 3. And that will give you a equal to 1/4. Okay. But to find the remaining constant b, you could either expand it out and make a pretty complicated expression, or you could just give some random value to s. What would be the easiest value to assign for s here? Other than 0 and 2, which we already used. What is your most popular number? 1. Okay. S equal to 1 will give you 1 equal to a. Okay, that's going to be 1 minus 2 whole square. It's just 1. This is going to be b times 1 times -1. That's going to be 1 a minus b plus c. Okay. And what we know are a and c. So a is 1/4, c is half, and the usual difficult part of adding fractions here. So 1/4 and a half is 3/4. Okay. And then you have 1 minus 3/4, and it's a negative b, so b is -1/4. Just keep an eye on the number and the sign. Okay, it's a -1/4. So relief if we get these numbers right. Okay. Okay, so plug it in, and that's going to be the Laplace inverse of 1/4 over S. I hope all of you have your Laplace tables next to you. Okay, we need this in a few seconds. Minus 1/4 over S minus 2 and plus 1/4 over, sorry, plus 1/2 over S minus 2 whole square. Okay, so there are three terms here. This looks like some constant K over S. Okay, that is case number 1. This looks like case number 3 because you have 1 over S minus A. Okay. 1/4 is a constant, of course. This is case number 3. The only new case here is this one. Which one does this look like? Case 2 or 4? I forgot. Something with 1 over S minus A to the power of, I think it might look like this, I forgot. What it looks like? Okay, so this is case 4. And when you see this, you should know that n plus 1 is 2, so n is 1. Okay. So let's do this term by term. That's going to be, the first would be just 1/4. Because the Laplace of 1/4 is 1 over S, 1/4 over S, so backwards it's 1/4. Minus 1/4 e to the power of 2t. You're going from the S world to the t world. Okay. Plus a half. So here n plus 1 is 2, so n is 1. Okay, and 1 factorial is 1. So we have what is the Laplace inverse for this according to the table? E to the power of t to the power of n, e to the power of at. Here n is 1. Okay, so it's going to be t to the power of 1, e to the power of a is 2. T. You don't have to write t to the power of 1, but just to be clear. Okay. Keep an eye on this term. That looks like what you typically would get for a repeated root when you solve your second order equations. Okay, so Mr. Laplace is taking care of all that stuff right away. Okay, so that is how partial fractions work for repeated factors. Okay. It's particularly useful when we solve differential equations with repeated roots, okay, because in that case you don't have to worry about linearly dependent and independent terms. It's all taken care of. All right. Any questions on that one? Okay, as promised, let me do one with completing the squares. Okay. Though I think most of the completing squares problems are kind of dumped into section 3.3 or something, but it's useful to know right away. So example 10, was it? I think we were kind of numbering all the examples. I forgot where we stopped yesterday. 9, 8, 8. Doesn't matter. You can put 85 if you want. Find the Laplace inverse of S over S square plus 12 S plus 45. Okay. And you should ask yourself questions when you see something like this. The first question is, can we factor this into nice numbers? You can factor this, but can we factor this into nice real numbers? Okay. Means can you find two numbers? So sum is 12 and the product is 45. No, right? If you go to the imaginary world, you could do it, but in the real world, you cannot. Okay. So then you don't stop. Okay, that is when the next option is completing the square. So it's always this, then completing the squares. You don't go to completing the squares and start doing it, as so that is the only option. Okay, the answer is this. Answer to this question is no. Then complete the squares. Okay. Because if you try to complete squares with terms which you could factor, it's not going to work. Okay. All right. So I hope all of you remember how to complete the squares. L inverse. This is an S, not 5. S over S plus 6 whole square, because half of 12 is 6. And that would typically give you S square plus 12, S plus 36. And then you have to add 9 to make up the 45. Okay. So the 45 was kind of cleverly designed, okay, to give you a perfect square there. Okay, now look at the table and tell me which one does this exactly match, or maybe almost exactly match. You need to have your Laplace table. Okay, without this, these lectures can be kind of really awkward. Is it an exact match to anything? No, right? Okay, so what is the closest match? Okay, so almost case. Is that the one with the S minus something in the numerator? Okay. Because you cannot create an S. Okay, there should be an S to start with. So almost case number 7. What we need is an S plus 6 here. Okay. And how do we make that happen? Okay, or add and subtract 6. L inverse of S plus 6 minus 6. Okay. Effectively, I haven't done anything, but I have done something. Okay. Over S plus 6 whole square plus 9. Okay. And the step that most of the students forget to do, just separate them out. Okay, don't cancel the 6 and negative 6, then you're back to square 1. You need to kind of group it like this, separate the two. L inverse of S plus 6 over S plus 6 whole square plus 9, which is 3 square, minus, I don't know how useful this 6 is going to be. Okay, either keep it inside or outside, that's up to you. L of 1 over S plus 6 whole square plus 3 square. Okay. Again, this decision of whether to keep it inside or outside, there is no correct answer to it. Okay, depends on each problem. Doesn't really matter as long as you don't make any mistakes. Okay. So maybe keeping it inside would have been better. I don't know. Okay. Now this is exactly case number 7. This one is almost case number 8. What is missing would be a 3 here, because the k over S minus a whole square plus k square. Okay, so to put that 3, you can divide a 3 and multiply a 3. That's what I said. You could have borrowed a 3 from the 6. Okay, so things that you could do if you are observant enough. Either way, it's going to be a 2. All right, now that is exact match to case number 8. So this is going to be, can somebody tell me online what the first Laplace inverse would be, the first term? You don't have to memorize it, just look at the table, take the appropriate values of A and K and tell me what will be. Just unmute and tell me, don't try to type it in. Okay. Go ahead. There are 23 of you here, so.
It's e to the 6t cosine 3t.
Almost.
E minus. Wait.
Minus. Good. And Somebody here can tell me the remaining term, minus 2 negative sine of 3t. And usually those are the terms you would expect in a damped oscillator, okay? The exponential and the sine cosine terms. So you can see what kind of functions you will end up getting when you do these problems using Laplace transform. Okay. The cases with repeated roots, the exponential sine cosine terms, okay, all with some simple algebraic manipulations. So that's kind of a motivation to do this in the context of differential equations. Okay. Okay, any questions about all these examples? So I think that was the 8th example we did. So we did cases with partial fractions, with linear terms, quadratic terms, repeated factors, completing the squares. These are the algebraic tools you need to do in chapter 3 for different, different cases. Any questions? All right, then let's jump into some differential equations now. So keep those algebraic things close to you and the table. It'll take a few minutes to get warmed up to this process of Laplace transform. First, you might think, oh, let me just do it using chapter 2. It's easier. Okay. But it'll reach a point where chapter 2 won't help you anymore. So that is where Mr. Laplace is super helpful. Section 3.2. Initial value problems. Using Laplace transform. So we'll mostly do first and second order cases. And once again, at this point, you could have done these using chapters 1 and 2. Okay. But we are just trying to learn a new technique here. So the first order would look like this: a y double prime plus b y equal to f of t, where y of 0 equal to some value, okay, equal to y1. That's the first order case, and the second order would look like a y double prime plus b y prime plus cy equal to f of t, with y of 0 equal to y1 and y prime of 0 y2. Okay. So the only drawback of Laplace transform, in addition to all the algebraic requirements, is that you need some initial values to do this. Okay. It really cannot give you a general solution. So that is the only problem with Laplace transform. Can only do initial value problems, okay, IVPs. Don't try to pull this count on Thursday's test. Okay. If I'm asking you to find a general solution, don't try Laplace transform because you won't reach anywhere. Okay. So we'll keep this for next week. So this week you can still do what you have learned in chapter 2. All right. So the question is then, what is the Laplace transform for these derivatives, y prime and y double prime? Well, it's in the table, but it's nice to know how to get those things first. Okay. So what is the Laplace transform of y prime of t? And y prime is the first derivative of y with respect to t. Okay. As always, if you don't know something, go back to your definition: 0 to infinity e to the power of negative st times y prime of t dt. Because right now I have no idea what this is. Okay. We'll do integration by parts here because there's nothing else we could do at this point. Okay, so let's call this as u, and this is dv. So integration by parts. Again, derivation is just for curiosity reasons. Okay, I'm not going to ask you derivations in exams or anything. So u equal to negative e to the power of negative st, and dv equal to y prime of t dt. Find the derivative of this. So du is going to be negative s e to the power of negative st. Okay, you're finding derivative, not antiderivative. And s is the constant here. T is the variable. V is the antiderivative of this, which is just y of t. So now we have both u and v. Okay, let's complete the integration by parts. That's going to be uv minus integral of v du. Which, when you plug in these items in there, will give you uv is the product of these two terms, okay, e to the power of negative st times y of t. Don't forget the limits are going from 0 to infinity. Okay, just going to cheat a little bit. I'm just going to plug in 0 to infinity without going through the limit process. Okay, I hope you will bear with me, because we're just trying to focus on the Laplace of the derivative without going into all the details. Okay. So that's your uv from 0 to infinity minus the integral from 0 to infinity of v du, which is the product of these two terms. That's going to be negative s e to the power of negative st times y of t dt. There should be a dt here. And you can factor this negative s outside, and that's going to give you positive s times the integral from 0 to infinity e to the power of negative st times y of t dt. Okay. That is this block. And then you have this plus the e to the power of negative st times y of t from 0 to infinity. Once again, the sloppy process of treating infinity as a number. Okay. What is this term here? You don't want to keep on doing this in circles. Okay. What does this integral here represent? Yep.
The Laplace transform of y of t.
Yeah, it's the Laplace transform of y of t. Let's just write f L of y of t. Okay. And we'll call it as capital Y of s. Just like we had f of t as capital F of s. Okay. Laplace of y of t, the unknown function, we'll call it as uppercase or capital Y of s. And all that remains now is this term plus e to the power of negative infinity, which is 0, okay, minus e to the 0, which is 1, times y of 0. So this 0 comes from this part. Okay. So you're getting an opportunity to plug in your initial condition right away. Okay, you don't wait till the end of the problem. Okay, the initial value of y of 0 goes in immediately into the question. So as soon as you start the first step, okay, it goes in right there. So the Laplace transform for y prime is going to be s times capital Y of s minus y of 0. And that is going to be case number 10 or 11, forgot. Oh, 9. What case is this in? Case something. Okay. L of y prime equal to s times y of s. Case 13? 14? Okay, thank you. It was undercounting then. S times y of s minus y of 0. You don't have to memorize it. Every time you do the problem, please just copy it correctly from the table. Okay. A lot of times students, they rely on their memory and then they miss this term or put a plus there. Okay. S times y of s minus y of 0. Again, this part here, this is just the Laplace transform of little y of t. And our objective is to find y of t. Okay, that is what the whole problem is about. So you shouldn't be looking for this in the table. Okay, that's what you're trying to solve for. And this must be given in the question and plugged in right away. Okay. You don't solve and then 5 minutes later you plug it in. You plug it in right away and solve. All right, so let's see how this works for a first order case. Okay. If you understand the process, it should work the same way for higher order cases as well. So the procedure is as follows. So the procedure to solve this initial value problem using Laplace transform. Okay. Step 1, take the Laplace transform from left to right of the entire equation. Remember that a and b are numbers. Okay, so those will have some values given in the question. So all you're doing is doing a times a Laplace of y prime plus b times Laplace of y equal to Laplace of f of t. Okay. And this is what you just did in case number 14. And this is capital Y of s. And this will be one of the cases from the table. Right? Look what happened. You just transformed a differential equation into an algebraic equation of y of s. Okay. So you have something like this now. A times sy of s. Don't try to memorize a general form. I'm just trying to write down what it looks like. Okay. This is case number 14. So a times sy of s minus y of 0 plus b times y of s equal to whatever f of s you get on the right hand side. So it's not a differential equation anymore, it's an algebraic equation. Solve for y of s algebraically. Step 2. And at that point, you can also observe that the value for y of 0 should be plugged in. Okay. So we have a sy of s minus a times y1. Okay, that is my y of 0 plus b times y of s equal to f of s. This is a typical algebraic equation. Okay. You don't need any nuclear weapons to solve this. So y of s would be, don't forget to bring this term to the right hand side first. Okay. F of s plus a times y1 divided by the coefficients of ys, which is as plus b. So that is what I mean when I say that solve algebraically for y of s. You will get something in terms of s on the right hand side. Okay. So if you have done some math in your life, you should be able to do steps 1 and 2 pretty easily. Okay. There's nothing complicated here, right? Copy from the table, solve for YFS. Everything going okay now. Step 3, take the inverse Laplace transform. And this is where you need to be algebraically prepared to take whatever techniques you need. Okay, so Y of t would be L inverse of YFS. So partial fraction, completing the squares, whatever things you need, you do it and retrieve your Y of t. So if there is anything that is a bit intense, it's going to happen in step 3, okay, because steps 1 and 2 are just ordinary things. Okay, so that is the process, and we'll follow the same thing even for second order equations. Okay, instead of first order, it will be a second order term here, but the process is the same. All right, so let's do an example. Any questions about the procedure or the algorithm for Laplace transform? Okay, so let's do an example. Again, for first order, it might look like an overkill. Example 1. Solve the initial value problem. I'm not going to explicitly write using Laplace transform, but I hope you understand you're doing that. So, okay, y prime minus 3y equal to 2 e to the power of 2t with y of 0 equal to 1. This is something you would have done using integrating factor in chapter 1. Okay, it's not a separable equation. So if you were doing section 1.4, it's a perfect candidate for doing integrating factor. Okay, but right now we are using the Laplace transform. All right, so step 1, take Laplace of the entire equation. It's L of y prime minus 3 times L of y equal to 2 times Laplace of e to the power of 2t. I would strongly recommend against using this as some kind of canned formula. Okay, just do the problem just based on what is given to you. Okay, don't memorize that or use that. So this is going to be SYFS minus y of 0 minus 3ys equal to 2 times the Laplace of e to the 2t. Case number 3 is 1 over s minus 2. And y of 0 is 1. Okay, so let's plug it in. So you get s minus 3 y of s equal to 2 over s minus 2. And then bring this over here. That's going to be plus 1. Divide both sides by s minus 3. Okay. That's 1 over s minus 3. Usually students have questions whether it's wise to combine in these two into a single term. Okay. There is no perfect answer to that. I would just leave it separately for now and just later if you have to combine it, you could do it. Okay. In general, it's probably not a good idea to simplify things ahead of time. So this is one term, this is a second term. Okay. And this is where we need partial fractions. Right, PF for partial fractions. So that is where step 2 will end, right? You have YFS equal to some expression, okay? And now comes the quote unquote difficult part of the problem. So step 3, let's find this first. This is pretty okay, right? This is case number 3 already. So we need to find partial fraction for 2 over s minus 2 times s minus 3. Both these are linear terms, so a over s minus 2 plus b over s minus 3. Nothing amazing going on here. It's just a pair of linear terms. So it's a times s minus 3 plus b times s minus 2. So if you plug in s equal to 2, you get a equal to negative 2 and s equal to 3, b equal to 2. So you could either do it on the side or you could just do it along with the problem. Okay, but you need this. Almost there, right? So y of s equal to the result from the partial fraction, which is negative 2 over s minus 2 plus 3, sorry, plus 2 over s minus 3. And you already had a 1 over s minus 3 from the initial value. Okay, so please don't forget it. Now you can combine these two. Okay, this is just 3 over s minus 3. I don't think you need my permission to combine these two. Sitting there waiting to be combined. Now this is case 3. That is case 3. Y of t equal to negative 2 e to the power of 2t plus 3 e to the power of 3t. You would have gotten the same answer if you did integrating factor. Okay. And at this point, it's difficult to kind of argue about which one is easier or harder. Okay. You might have your own opinions about it. But this section is just to show you the process before we start doing the more unique features of Laplace transform. Okay. So that is the final answer. It's a unique solution because the initial value was plugged in. Okay, there is no arbitrary constant lying around. So you can see the integrating factor is e to the power of 3t from the p of t equal negative 3. All right. Any questions there? Now let's look at the next case. Okay. What is L of y double prime? Because first order equations are boring. So let's focus our attention on second order equations. Again, I don't know what this is, so I'll start with integrating by parts. But we already know the Laplace for s prime, okay, or y prime. So this is my u and this is my dv. And you have du equal to negative s e to the power of negative st and v equal to y prime. One derivative lower. Okay. So this is going to be uv, which is e to the power of negative st times y prime of t and I'm going to cheat a little bit from 0 to infinity. Okay. Minus the integral from 0 to infinity v du, which is y prime times this term. Okay. And that's going to be plus s times 0 to infinity e to the power of negative st times y prime of t dt. You know this one. This is your case 14. Okay, L of y prime. So you don't have to do that all over. Okay. So it's going to be s times y of s minus y of 0. Okay, and there is an s waiting out here, so you need to distribute it over. And this term here will give you 0, like we had earlier, okay, minus y prime of 0. So there are the two boundary values now, or the two initial values, right? Y of 0, y prime of 0. So Laplace has perfect spots to plug in those things and just get started right away. Okay. So we have s square y of s, then you have a minus sy of 0. Okay. You have to distribute this to both the terms. It's going to be s square y of s minus sy of 0 minus y prime of 0. Probably the worst location to write it, so let me write it once more. So case number 15, I would guess. So, or is it just 14 part B? Forgot. I don't know if I listed it as a separate case or either way. L of y double prime equal to s square y of s minus sy of 0 minus y prime of 0. Things that usually students forget to copy correctly, they sometimes miss this s here. Okay. That could give you wrong answers, and also both these terms are negative. Okay. So you have to input both initial values and be a bit careful when you move these terms around. Okay. Unlike the first order equation, there are two terms to be moved, so just watch out. Okay. Same process though. All right, so let's start with a nice, simple, homogeneous equation, and then we will make it worse. Okay. Example 1, y double prime plus 3y prime plus 2y equal to 0, y of 0 equal to 1, y prime of 0 equal to 1. Okay. Again, you cannot do this without the initial values, so if you need them. You know the answer to this, right? From section 2.3. You know what the answer looks like. Okay. It should be c1 e to the power of negative t plus c2 e to the power of negative 2t. You know the characteristic equation, quadratic, and all that stuff. Okay. Did you do it right? Oops. But let's forget about that and let's focus on Mr. Laplace. Okay. So this is going to be L of y double prime plus 3 L of y prime plus 2 L of y. Laplace of 0 is 0. Okay. So it's s square y of s minus sy of 0 minus y prime of 0. Okay, that is the entire L of y double prime plus 3 times sy of s minus y of 0. Okay, that is the Laplace of y prime, case 14, plus 2 y s equal to 0. So in this problem, y of 0 is 1, y prime of 0 is 1. Okay. Don't forget this thing here. Okay. It's not just in the y double prime. You also have a y of 0 in here. So plug it in. And when you do the remaining steps, you need to be careful about distributing the 3 inside. Okay. There are small things that students usually miss when they do this kinds of problems. So distribute the 3 inside here and to this term. So let's try to group the terms with y of s on one side and all other terms to the right hand side. So it's going to be s square plus 3s plus 2 times y of s. Okay. Those are the terms multiplying capital Y. The remaining terms, I'm going to take it slow here because I don't want to make mistakes. Okay, so it's minus s minus 1. Then you have a minus 3 equal to 0. So it's a minus s minus 4, which when you move to the right side becomes s square plus 3s plus 2 times y of s equal to s plus 4. This pair of terms, is s and 4, came out of the initial values. If both y of 0 and y prime of 0 was 0, the solution would be 0. So y of s is equal to s plus 4 divided by s square plus 3s plus 2. One thing we should always observe in these problems is that this is the same as your characteristic equation from chapter 2. Okay, always. So in section 2.3, the characteristic equation would look like this: r square plus 3r plus 2 equal to 0. Okay, so you can see the similarity here. Okay, that always should be preserved. Whatever you would expect in the characteristic equation is what you have in the y of s term. Which is why I was able to write the solution there, right? Okay, so this one we could factor as s plus 4 divided by s plus 1 times s plus 2. Partial fraction. So s plus 4 over s plus 1 times s plus 2 equal to a over s plus 1 plus b over s plus 2. It's the degree of the terms in the denominator that decides what you write in the numerator. Okay, whether this is s plus 4 or whatever, that shouldn't affect it. Okay, if it is a higher degree, then we have a problem, but we won't get those kinds of situations here. So clear the denominator, so it's s plus 4 equal to a times s plus 2 plus b times s plus 1. All right, so as usual, plug in some convenient values here. S equal to -1 gives you a equal to 3, and s equal to -2 gives you b equal to -2. Okay, so that is the partial fraction work I needed for that question. So what I'm going to do is I'll just make use of whatever space I have here. Okay, that's going to be 3 over s plus 1 minus 2 over s plus 2. So we have both the terms ready to be inverted. Okay, case number 3 will give you y of t. But it came with a bonus. You also have the C1 and the C2 values. Okay, that is the advantage of Laplace transform. We don't have to kind of go back and redo it for the constants. So it's going to be 3 e to the power of -t minus 2 e to the power of -2t. Okay, which agrees with whatever I wrote somewhere here for the expected solution. All right. Any questions? Again, it might look like an overkill at this point. You might think, oh, it's much easier to do in 3.2. Right? Example 3. Let's do a non-homogeneous case. Okay, y double prime plus 4y, not y prime, equal to, I don't know, sine of 3t with y of 0 equal to 0 and y prime of 0 equal to 0. This looks like a spring mass problem with no damping, with an external force with no resonance. Okay. Can you start doing this and see how it goes? So, same process, take Laplace transform and keep going, and I'll follow up. Okay. Okay, so take Laplace for both sides. Okay, the left-hand side only has 2 terms. So the first one has the second derivative. And luckily here, these 2 terms are 0. Okay, that's always welcome. That's one less headache to handle. Okay. And this is here. There is no s multiplying the y of s for this term. Okay, just for y of s. And this is case number 7 or 6. 6, 3 over s squared plus 9. Okay, so this is, as I said, this represents a spring mass problem with no dash part and external force starting from equilibrium. Okay. So we have y of s equal to 3 divided by s squared plus 9 times s squared plus 4. Please don't factor this as s plus 3 times s minus 3. Okay. Hopefully that is clear. All right, partial fraction time again. 2 quadratics, so we need special treatment. So 3 over s squared plus 9 times s squared plus 4 will be sum as plus b over s squared plus 9 plus cs plus d. Okay, please don't reuse the same constants here, it'll be confusing. Okay, don't use as plus b again here. Cs plus d over s squared plus 4. So if we were doing this in chapter 2, we would be doing xh and xp separately and then plugging in the initial values. Okay, so we're taking care of all of these things at the same time. So clear the fractions. That's going to be 3 equal to as plus b times s squared plus 4 plus cs plus d times s squared plus 9. We have 4 constants evaluate here. Okay, so you should be a little bit careful about how you do this. The safest way to do this is to just expand it out, as bad as it sounds. Okay, at least you will have a definite idea about what is going on. Okay. So just multiply this out. That's going to be as to the 3 plus bs square plus 4as plus 4b. So I'm just keeping the terms in decreasing order of degree. And then you have c s to the 3 plus ds square plus 9cs plus 9d. Okay. I know that looks awful, but the left-hand side is rather easy for us because it only has a 3, which also means that all the other coefficients should be equal to 0. I'm just keeping placeholders for the remaining terms, s to the 3, s square, s, okay, they're all multiplied with 0. This is the safest way to do any partial fraction problem. There is no trick involved. Okay, just need to set it up and compare the coefficients on both sides. The right-hand side would become a plus c times s to the 3. Okay, that is combining those two, plus b plus d times s square plus 4a plus 9c times s. Okay. And the last term is a precious one because that is what is going to keep this non-zero. Okay. Plus 4b plus 9d. So now compare the coefficients of this term or this set of terms here and all these terms on the left-hand side. Okay. So compare the coefficients of s to the power of 3 and you get a plus c equal to 0. The s square terms will give you b plus d equal to 0. The s terms will give you 4a plus 9c equal to 0. Okay. And just when you think that everything is 0, the last set of terms is not. Okay. 4b plus 9d is equal to 3. The constant term. I'm going to make a huge claim here. Okay. I'm going to say that based on these two equations, the only possible case is that a and c are both equal to 0. Do you agree? Should be obvious, right? You cannot have any other non-zero number to give you 0 on the right-hand side for those two. Okay. You can check it yourself. That leaves us with this equation, which is b equal to negative d. Plug it in here, and you get negative 4d plus 9d, which is 5d equal to 3. So d is 3/5 and b is negative 3/5. Okay. So we started with four constants, and based on whatever we had in the problem, we got rid of two of them. Okay. So we only have two remaining. And let's try to bring it back into our YFS expression, which was right there. Okay. So it's a perfect spot. So this is what we were doing. So YFS would be A was 0, B is negative 3/5 over S square plus 9, plus C is 0, and D is positive 3/5 over S square plus 4. Don't forget, we are expecting your X to be equal to XH plus XP from chapter 2. Okay. Your XH based on the homogeneous equation should have been C1 cosine of 2t plus C2 sine of 2t, and your XP should have been some A cosine 3t plus B sine 3t. We are doing all of these things at the same time when you do Laplace transform. Okay, so almost there. Okay. So if you take the inverse Laplace of this, y of t, this is going to be negative 3/5 times the inverse Laplace of 1 over s square plus 9. Going to do this slowly. Okay. Maybe it's nice to keep this 3 inside, just to, that might help actually. And it's your choice. You can play with those numbers as you like. Okay. You can keep it outside, inside. This one, there's not anything useful by keeping it inside. So let's throw it out as in here. This is perfect, right? Case number 6. This is going to be sine of 3t here. So it's going to be negative 1/5 sine of 3t. It should have been your B here. Okay. That is your particular solution. And then you have 3/5 times. Okay. Need some manipulations here. You expect a 2, so you multiply and divide a 2. So that it's a perfect match with case number 6. Okay. So it's 3 over 10 times sine of 2t, which is this part. So you didn't have to worry about what I would guess for XP. Is it going to be linearly dependent, independent? No such headaches. It does all these things. The headache is the partial fraction. Okay, if you don't like algebra, then it's a problem. Okay. All right. Any questions on this? Be careful about quadratic partial fractions. Okay, it's not a over s squared plus 9. It's as plus b. Okay, common mistake. Four. Y double prime plus 4y prime plus 4y equal to 4 e to the power of 2t. I think I'm being a little bit ambitious here. Let's see. Y of 0 equal to 0. Y prime of 0 equal to 0. Yeah. All right. Can you start and then see how it goes? change this to a -4 just so that it gets more exciting. Otherwise, it'll be slightly boring. So just change that y prime term to a -4. Sorry about that. Okay, so this is going to be s square y of s minus sy of 0 is 0 minus y prime of 0 is also 0. Okay, minus 4 times sy of s minus y of 0 is again 0. Okay, plus 4 y of s equal to 4 divided by s minus 2. Okay, that is written after plugging in the initial values. Okay, it looks incredibly compact because I did not plug in all the zeros. Okay. So we have s square minus 4s plus 4 times y of s equal to 4 over s minus 2. And I've written some stuff here just to remind you about how we would have done this in chapter 2. Okay. The characteristic equation is r square minus 4r plus 4, which is what we have here, s square minus 4s plus 4. Okay. That will give you a repeated root. So you had to be careful about linearly dependent terms and write it as c1e to the 2t plus c2t to the 2t. And then you have to make a guess for a yp. And that should be a t square because if you write t, that will be dependent with this. Okay. So all kinds of things here to keep in mind. Let's see what this will give you. Okay. The problem is made slightly easy because of the 0 initial values. Okay, that made the problem a little bit more compact, but nevertheless, this becomes y of s equal to 4 divided by s minus 2. Okay. And this is just s minus 2 whole square. Which is 4 divided by s minus 2 to the power of 3. Okay, there is no need for partial fraction or anything here. Okay. Just one term. And if you look at case number 4, I think, okay, you have Laplace of t to the power of n e to the power of at equal to n factorial divided by e to the power divided by s minus a to the power of n plus 1. Here, a is 2, okay. N plus 1 is 3. So n is 2, okay, and 2 factorial is 2. So this can be written as 2 times 2 factorial, which is 2 over s minus 2 to the power of 2 plus 1. Okay, just to kind of lead you into the answer. Okay. And what is that equal to? What is the Laplace inverse of this? So this 2 is here. What is the remaining term? Yeah. Uh-huh. A is 2, right? So e to the power of 2t. That's what you would have expected here, okay, without any headaches. Right? Of course, it looks super easy because these two values were 0. That's why we didn't have to do any partial fraction or anything. If one of these was not 0, then you have to add those in. Okay. But still, you have to give credit to Laplace to get exactly the same answer as you would get with Euler's guess. Okay. All right. Any questions? So this also tells you that your C1 and C2 values were equal to 0 and your A is 2. Okay. So you don't have to dissect your answer, but just I'm telling you that this was there, but they kind of fell out because of the initial values. Okay. Okay, I hope all of you are comfortable with the process now. Okay, so section 3.2 is just redoing chapter 2 kind of problems with Laplace transform. Okay, there is nothing really new there. Okay, so all the new stuff comes in section 3.3, and this is where I want you to pay attention. Okay, things are a little bit rough in 3.3 because there are some rather weird concepts to get used to. Okay. All these things are still there, but we need to apply Laplace transform to cases where your typical calculus usually breaks down. Okay, that is what we're going to do next. So section 3.3 and 3.4. I do this together because it kind of covers all the things you need in 2 different sections, but you could just combine them. Okay? But it's going to take today, tomorrow, Thursday's lecture, whatever time we usually take. Okay? And hopefully by then I'll be done. If not, I'll finish it off on next Tuesday. No lecture on Monday. Okay? 15 theorems. And discontinuous inputs. If there is anything in this course which is anything close to what people call as difficult, it's this part. Okay, if you can survive this, you're good. Okay. All right, so let's talk about the shifting theorems first. Okay, the first shifting theorem, which we will quickly do and get out of our way. And before I write the statement of the theorem, let me ask you, based on whatever you've observed so far, if you look at case number 2, okay, which probably looks like this, and case number 4, which looks like that's the one I just wrote there. Okay. Hope I'm writing this correctly. I'm also going to pair up case number 5, which is the Laplace of, let me know if this is not the right one. Okay. Is that the right one? Okay. And case number 6, And if you look at cases 7 and 8, okay, they're kind of just derived out of this. Okay. Case 7 is with e to the power of at cosine kt, and that has got an s minus a here. Sorry for that. And similarly, case number 8 is k over s minus a whole square plus k square. If you just look at these Laplace transforms, okay, pairwise, what do you observe happened from case 2 to case 4, case 5 to 7, and 6 to 8, other than the fact that the case numbers are shifted by 2? You know? So anything else that you're observing here? If you observe that, you know, the first shifting theorem is taken care of. What am I doing from case 2 to case 4? What is different? We just, yeah. Yep. So all these cases I'm multiplying by e to the power of at. And what changes on the Laplace transform?
Subtract by a.
Yep. You're shifting that s by a, right? Anytime there is an s here, that is shifted by, so when you subtract, you're kind of displacing or shifting it by that a value that you are adding here. Okay. That's it. So the first shifting theorem says that if Laplace transform of f of t equal to capital F of s, then Laplace of e to the power of at times f of t equal to f of s minus a. Okay, simple enough, right? So there is nothing remarkable about this. Okay, we are not really going to say using first shifting theorem because these cases are already in the table. Okay, but when you say shifting theorems, usually this is the first one mentioned. So I have to write that down. And the reason why this happens is because of a simple change of variables. Okay, there is no wow factor here. So just to quickly show you why this is the case, the integral of Laplace of e to the power of at times f of t. Go back to definition, 0 to infinity e to the power of at times e to the power of negative st dt. Okay, this is my f of t dt. You can combine these two into a single exponent, and that's going to be 0 to infinity e to the power of negative s minus a times t times f of t dt. It's almost there now, right? You're just calling this as a new variable, so you can call, say, v equal to s minus a times t, of course. Then you have the integral from 0 to infinity of e to the power of negative vt times f of v dv, and that is what you have, capital F of v, which is capital F of s minus a. And so it's a very simple change of variables that happens there. Okay, there's nothing extraordinary. Okay, so nothing to worry about for the first shifting theorem. Okay, so anything that comes after this is where all the new material comes in. And please pay attention to this. Okay, a lot of students have trouble understanding what happens with these functions, piecewise continuous functions. So you probably would have seen this when you first took a calculus course. Okay, function need not always look like this. Okay, this is what you call as a fully continuous function. It might be broken down into pieces like this. Okay. It's okay, right? You can have bits and pieces of functions which are continuous here, but there's a gap here. Okay, that is what a piecewise continuous function means. So a function of the form f of t equal to, assuming that t is always positive, f1 of t, where t is between 0 and t1, f2 of t, where your t is between t1 and t2. So I'm going to include the left endpoints in the interval, the right endpoints are not included. Okay. f3 of t, t2 less than or equal to t less than t3, and so on. You can have any number of pieces kind of glued together to form a piecewise continuous function. The most common example or the most famous example for this would be the following. F of t equal to 0 for t less than a. Again, it starts from 0, so 0 less than or equal to t less than a, and it's equal to 1 for t greater than or equal to a. So let's see what the graph of this function looks like. If you try to do this using a calculator, it looks funny because it's got two pieces, so you have to be careful. Okay. So this is your y-t axis, or the f of t versus t. A is somewhere here, okay, assuming that we are going in the positive t direction. A is somewhere on the t-axis. What it's saying is that till you reach your value of t, this is equal to 0. Okay. And once it attains a value of t equal to a, it jumps to a value of 1. Okay. So it's a hollow circle here, solid circle here, and the dashed line just to show that it's 1. That is what the graph of this function looks like. Okay. You can see why it's a discontinuous function, because there's a jump from this to this. It's a 0 up to here, 1 up here. Okay. And I hope all of you are used to this notation of a hollow circle and solid circle. High school, hollow for not including, solid for including. Okay. This is what you call as a unit step function. The word unit stands for 1. Okay, it's a step function because it's almost like there is a step there. Okay. This is also called the Heaviside's unit step function. Probably the most famous self-taught engineer, okay, who did very good discoveries in mathematics applied in his field over that time, okay, which became very useful later. Okay. Oliver Heaviside. So his idea was this: if you want to apply math to something that you use in real life, okay, you need to have some specific notations and other ideas which might sound crazy, but which is doable. Okay. So for example, if you want to keep something off for the first 10 seconds and then turn it on, right? That's something you might want to do. Okay, the signal is not going to be applied throughout the time. Okay, you want to turn the switch off and then turn it on. Okay, this is what you would do. So it's called the Heaviside step function. It's denoted by u of t minus a, u for unit. Okay. Some textbooks also, just to kind of give credit to Heaviside, call it as h of t minus a. This t minus a is just to tell you that it is kind of shifted by that value of a. Okay, it's not a u times t minus u times a. Okay, this is just a notation, it's not a multiplication. Okay. So, definition. The unit step function also called the Heaviside function denoted by u of t minus a. It's equal to either 0 or 1. It's a binary function, right? It's either off or on. Okay, that's the beauty of this function. So 0 for t between 0 and some value of a. Okay, that a is what is given here. So this is an indicator of where it is actually going to shift from 0 to 1. Okay. And this from a to infinity or t greater than or equal to a. Very simple thing. Let's try to understand this by combining some Heaviside functions and drawing some pictures. Okay. So sketch the function. F of t equal to 3 times u of t minus 2 plus 7 times u of t minus 8. Okay. Let's start with 2 pieces and then we will make it more complicated. When it says sketch the function, you're just going to get broken pieces of straight lines. Okay, this is not going to give you any pretty pictures. Okay. What you need to understand is this value is equal to 0 for t less than 2, and it's equal to 1 for t greater than or equal to 2. Okay. So that switch is not turned on until you hit t equal to 2. Okay. The switch is off till t equal to 2. We turn it on. Okay. And that force or the signal has a strength of 3 units coming in. That's the meaning. This is still off. Okay. This does not turn on till you hit t equal to 8. So this is 0 for t less than 8, and it's equal to 1 for t greater than or equal to 8. So when you do this for the first time, it's nice to kind of clearly write it in pieces. Okay, so it's equal to 0 for t less than 2, okay, because both switches are off. Okay, this is switch 1, that's switch 2, both are off. Okay. Then the first switch is turned on, second one is off. Okay, that's going to be 3 for 2 greater than or equal to t, 2 less than or equal to t less than 8. Okay. Because you have this is on, this is off. Okay. Next, both are on. That's going to be the first one, which is already on, 3 plus 7, which is 10 for t greater than or equal to 8. So that's how you convert a sum or a difference of step functions into a piecewise continuous function. Okay. Now you can sketch this because, so 3 pieces, 0, 3, and 10. So the sketch will look like this. This is your t-axis. The breakpoints are 2 and 8. Okay. Doesn't have to be drawn to scale. So something that represents 2 and 8. Remember, when you start the problem, there is nothing. Okay. No switches are on till you reach t equal to 2. So this is 0 here. You don't have to write 0 there, but there is a line there. Then between 2 and 8, it has strength 3. So this is a hollow circle here, a solid circle here, okay, because of the equality sign on the left side. And that is of strength 3. Okay. So this is 0, 3. That's a step there. Okay. And now both the switches are on. So after t equal to 8, we have both is combined, so 3 plus 7 is 10. So that's going to be starting from here and going to infinity. Okay. There is nothing in the problem that tells you it's stopping somewhere. So once it hits 10, it just goes forever. All right, so don't worry if this looks a little new and unfamiliar. Okay, so we'll do a few more examples tomorrow, and then we'll see what Laplace transforms can do with these kinds of situations where the input is kind of in bits and pieces and not continuous over time. Okay. All right, I think I'll stop there. And if you have any questions, I can wait for some time.
Thank you.
Thank you.